Hi everyone, and welcome back to another video about limits. Today we're going to be talking about continuity and how limits and continuity go together. And remember, to be a continuous function, you need to be able to trace that function all along its domain without picking up your pencil on a graph. But we're going to talk a little bit more about what it means to be continuous and define continuity. And we're going to look at some good stuff. So first things first, I would love for you to pause the video here in just a moment, and I want you to try to make a sketch of a graph that has these elements here listed to it. See if you can hit them all in one graph. And you know, there's more than one way to do this. There's more than one correct graph. So see what you can come up with, and then unpause the video and we'll see what it's supposed to look like. So let's take a look. When I have a limit, this first quality here, limit approaching negative infinity. Now remember, anytime we're approaching an infinity, I want you to think horizontal asymptote. So that right there means that we must have a horizontal asymptote. So approaching negative infinity on the left, that means I'm going to have some sort of, you know, at 2 on the left-hand side, I'm going to have a horizontal asymptote. And on the right-hand side, I'm going to have another horizontal asymptote at -1. So I'm going to put some dashed lines in there just to kind of remind me I'm going to have some asymptotes there. Now, the next thing says the limit approaching 0 from the left and from the right are these infinities. So now when I see that, that is an indicator. When I have a limit equaling infinity, that's an indicator that I'm going to have some sort of vertical asymptote. So this first one says approaching 0 from the left. So coming from the left, approaching 0, that means my graph needs to kind of go up towards positive infinity. And approaching 0 from the left, I need to go down towards negative infinity. So right now I don't even have a graph, but what I'm doing is I'm making little notes, and maybe you should do this lightly with your pencil to make notes. Your graph needs to go in this direction. Now, this next one says the limit as x approaches 2 from the left is the same as the limit approaching 2 from the right, and it's -3. So this tells me that the limit approaching 2 from the left and from the right is at -3. So I'm going to go over here. This is kind of tricky. 2, -3, I'm going to have something there, and it's going to be a connected graph like that. So now this is actually what my graph looks like. Maybe I should use the rainbow pen to denote that. There we go. Now I'm going to fill that dot in maybe, but first I'm going to go down here and say, oh, f of 2 was 4. That's curious. F of 2 is 4, but the limit is different. So that tells me that I should be leaving that an open dot at -3. It's connected there, but then I have this like random dot up here, f of 2 is 4. And now I think I have enough to complete my graph. I know that I have to approach that horizontal asymptote, and then here I'm going to approach the vertical asymptote. I'm going to do the same thing up here, and this must be the way the function looks. So I've got my horizontal asymptote, my vertical asymptote, open dot, and a solid dot there at 2, 4. So what's going on here is that we have a hole in our graph, and so describe anywhere that the function is not continuous. It's not continuous at x equals 2. We only use x to describe where we're not continuous. And I want to talk a little bit about some notation. And as we talk through this, we're going to be getting into using what's called interval notation. And interval notation says that when I describe something, I'm going to describe it. It almost looks like a set of ordered pairs. And so what I'll say for now is we're going to describe it where it's not continuous by identifying the 2 spots and saying, well, where x is 2, it's not continuous, and also where x is 0. Now, what that means is that the numbers 2 and 0 may or may not be part of the domain. So 2 is technically in the domain because we do have a y value. It's just not continuous there because I have to lift my pencil and jump up to it. But right now, my graph has 2 spots of discontinuity at 2 and 0. Now, remember, as we talk about continuity, it's all about definitions. And so when we talk about being continuous, we want to make sure we understand what's happening with continuity. So here's my official definition of continuity. A function is continuous at an interior point. And we'll go back up and look at that graph here in just a moment. At an interior point C, so not an end point, so some point in the middle of an interval, if the limit as x approaches that number is the same as the y value. So let's talk about what that means. Up here, we were not continuous at x equals 2. And what's happening here is that the limit as x approached 2 was -3, but it did not equal f of 2 because f of 2 was equal to 4. So the definition of continuity says that the limit and the y value agree. Remember, a limit can exist even if a y value doesn't. So for example, looking here, my y value is something completely different. I have a hole there. The limit describes what is y trying to be. When y gets to what it's trying to be, then we say it's continuous at that point. So when y gets to be what it wants to be when it grows up, we say that it's continuous. So again, the limit says what is y trying to be, f of x says what is y actually, and when those two things agree, then my function is continuous. So you might be asked on your AP exam to describe if a point is continuous or not. And the way that you're going to justify that answer is you will often refer to the limit, and you'll say, well, the limit approaching that spot is not the same as the y value, therefore by definition it is not continuous. So you need to know your definition. So I would pause and jot this down. Now, we know that a function is continuous at an endpoint. So suppose you have an interval between x equals a and x equals b, which, by the way, we write interval notation like this. So an interval would be like a to b. This would be endpoints included. And then if we use rounded brackets, a and b, endpoints not included. Now, let's talk about how this notation is going to help us decide if we're continuous at endpoints. You can be continuous at endpoints if, here's the definition, the limit as x approaches a from the right, so that's the left-handed interval. So here's your interval. Here's another interval. We'll close the dots. So this would be the closed interval. This would be the open interval picture. And so we know that on a closed interval, if this is a and this is b, those are your x values. As we're approaching a from the right, so as I'm going this way towards a, if the limit, if y is approaching something and that something is the same as the y coordinate, then you're continuous. Over here on b, if you're approaching b from the left, same deal. If what y is approaching is the same as the actual y value at the endpoint, well then you're continuous. And here's a good way to think about it. If the endpoints are closed dots, we're continuous there. If the endpoints are open dots, you're not continuous. That's really kind of what it boils down to. So if you have these closed brackets, we're generally going to say we're continuous. If we have the open brackets, we're not. And it all has to do with having a hole there. So if you have a hole in your graph, whether it's at an endpoint or on the interior, y is trying to become that y coordinate, but it never gets to be there. Only if the y coordinate and the limit agree at that spot do we have continuity. Now, you can have continuity in one of two ways. You can have continuity over a whole function. A function is continuous over the whole function if it is continuous everywhere in its domain. So what that means is every x that has a y that goes with it, as long as you can plug x in and get an answer back, and you don't have to lift your pencil, the whole function is considered a continuous function. You can also have continuous or continuity over an interval. It's continuous. A function is continuous over an interval if between the two endpoints there's no discontinuity. So let's talk a little bit more about these situations and see some, visuals to help us really get this concept down. Because if you're like me, you need to see it, and so we're going to see it now. If a function has discontinuity on an interval, here's my question for you. Can the overall function still be considered continuous? So if I have a hole or a vertical asymptote, maybe I wouldn't be continuous on the interval, but could I still be a continuous function? Well, let's explore this. So here we go. Consider the following graphs and identify any discontinuity, then state whether the function is continuous. So before we even look at the graph, let's talk a little bit about what's going on with each of these. Now, question A has this 1 over this value, and so immediately when I see a fraction, I think, oh, there's probably some sort of asymptote or hole or something like that. And this one actually doesn't have any asymptotes or holes because there's nothing. Actually, I take that back. X equals -2. It was staring me right in the face. X equals -2 is going to be some sort of vertical asymptote when I look at the graph. And so I'm going to have some discontinuity there. So I know that at -2, there's something happening. So just because I have a discontinuity there, does that mean that I can't call this a continuous function? We'll come back to that. Let's take a look at this guy. So we've got the cube root of 2x. Maybe there's nothing there. Maybe there's no problems. I don't think there's anything. I can cube root a negative, right? So there's no discontinuity, nothing there to worry about, and we'll confirm it with the graph. And then over here, question C, we've got the natural log. Now remember, you can't take the natural log of 0. That does not exist. So be careful about that. You try to do it in your calculator. Remember, what you're doing is you're saying e to some power is equal to 0. You can't have an exponential function equal 0. It's never going to be 0. So what would make this 0? X equals 2. Ooh, but what is it? Is it a vertical asymptote? Is it a horizontal asymptote? What does it look like? Well, we're going to look at the graph. I said it in a previous video all about natural log and what happens there, but we'll take a look at the graph. You might already know. So when I go and I look at these graphs and I pull them up in Desmos, here's what they kind of look at each one at a time, kind of confirm what we said. Now, here's the first one. We have a vertical asymptote at -2, like we said. But here's the cool part. If I'm going to describe the continuity of this function, I can describe it in one of two ways. The first thing I can do is I can say, is the function continuous? So that means the whole function over its entire domain. Now, if you have a vertical asymptote or a hole, this is not in the domain. Remember, to be in the domain, you need to be able to plug it in and get something back. It's not part of the domain. So the domain here is technically all real numbers except for -2. So this is a continuous function. But is it continuous on the interval -2 to 2? And the answer is no, not on -2 to 2. And the reason why, and if we look at the graph, is because of that vertical asymptote. It's not continuous. And remember, this is a closed interval. This means x between, for all values, here's another way to write it. This is what this interval notation with those closed brackets means. It means we're going to include 2 and -2 in there. So when I go to my graph here and I try to look at, between 2 and -2, because at that endpoint, I'm not continuous, on that closed interval, I'm not continuous. However, if I open the interval, all of a sudden, and you don't have to have both ends open, you could close that or leave it open. So if I don't include that -2, all of a sudden I'm continuous on that interval. So paying attention to whether your bracket is closed or open is going to make a difference in your answer, yes or no. So again, at that vertical asymptote, if I have a closed bracket, that square bracket, I'm not continuous on that interval. But the minute that I open it up and I don't include that as part of the interval, everything up to but not including that, yeah, I'm going to be continuous. So now let's take a look at this next function. We'll go ahead and pull that up on our graph. Here it is in blue. All right, so here's my function, and as I look around, there's nothing that I can't plug in. My graph continues on forever in both directions. There's no holes. There doesn't appear to be any kind of vertical asymptotes. So if I was going to consider this function over its whole domain, I would say that yes, it's continuous. If I'm going to consider it on the closed interval 2 to negative 2, yes, it's continuous, because at those endpoints, the values exist and the limits and the y values agree. The same thing is true on the open interval. When I come up here, I'm going to say that yes, it is absolutely continuous on everything. It's continuous everywhere. Yes on this closed interval, negative 2 to 2, and yes on the open interval. If it's continuous on the closed interval, it's more than likely continuous on that open interval. So now let's take a look at this last one here, this natural log function. Get that graph on there. So here we've got this green graph. Oh, it appears we have a vertical asymptote for this function, and if I zoom way out, you'll see. And the reason is because we can't take a log of a negative, can't take the log of a 0, we also can't take the log of a negative. So you think about it this way, e to some negative number, e to some number equals a negative, not going to happen. So there's no function, no value you could plug in to turn an e into a negative number. It just doesn't work. So we've got this vertical asymptote here. And so here's the question, am I continuous over the whole part of its domain? And the answer here is yes. Even though there's a vertical asymptote, those values over there on the left side of the vertical asymptote are not part of the domain. Those values create a negative inside of that parenthesis. It's not part of the domain. When you plug them in, you can't get an answer back. So overall, this logarithm function is continuous. So we'll say it's continuous function. But now let's look at the intervals. On the closed interval, negative 2 to 2, what's happening? Well, on the closed interval, negative 2 to 2, there's no function, there's no graph. So you can't, there's no way. So that also means that it's also not continuous on the open interval. So that settles that. So the idea here is that I want you to understand that you can be continuous as a function and still have discontinuity. That sounds really weird, but you can be continuous as a function and still have things like vertical asymptotes and holes. Now, just to make sure that we really drive this home, an example of a function that is not continuous everywhere would be a piecewise function. So it's possible that you'll have a piecewise function that maybe is not connected. So this would be a discontinuous function. But if it's connected, and as you're graphing it, not all piecewise functions are going to be discontinuous. Again, it has to do with, as you're dragging your pencil, do you have to jump? So you can have a continuous function that is continuous everywhere on its domain, but still have some discontinuity in there. So while we think about functions as, oh, when you lift your pencil, you know, if you have a vertical asymptote, the overall function, the big picture is that it's a nice, smooth, continuous curve. It just has that one asymptote. So we would call it a continuous function. However, we would identify the interval and say, well, you have a vertical asymptote here. So on this interval, we're not continuous. But as a big picture, then we can say that, yes, it could be continuous. So let's talk a little bit about removable discontinuity. When we do have a function that has a discontinuity, what do we do with it? Well, usually removable discontinuities are going to be what we call a hole in the function. So here, for example, if I factor this into x, let's see, minus 6, x minus 1, we can see that because these factors do cancel, here we go, these two are going to go away. I get what's called the extended function. So we have a hole at x equals 6. So the extended function looks like this. You just literally cancel the two factors, and whatever's left, well, that's your extended function. And we've talked about this before. So this guy here is your extended function when we cancel out the factor that creates the hole. Now, if you graph this f of x and you graph the extended function, they will look identical on a graphing calculator. They'll both be a line. And so what you're going to do to fill the hole is you're going to say, well, what's this function? I'm going to plug in x equals 6, and I'm going to get y equals 5. So the location of the hole is actually at the point 6, 5. So to create a function that fills the hole, what we do is we build a piecewise function. We say f of x equals, and then we say x squared minus 7x plus 6 all over x minus 6 for every value except x not equaling 6. And then we say, well, then we're going to let it equal 5 when x is 6. So what we've just done is we have filled the hole. We found the extended function. We plugged in the value of y equals 5, of x equals 6 to get y equals 5, and we've filled that hole. And so let me just take a moment, and I'm going to show you the graph and show you that this does, in fact, work. And so here we are looking at that function that we filled the hole for. And again, if you just kind of like go into Desmos and get to 6, you'll see that on the red function, it's completely undefined. But then if I turn on the blue and just watch closely, turn the blue on, turn the red off, it's the same exact line. And the only difference is that when we get to 6, the point is defined. And so what we do is we say, well, to fill up that empty hole in this red function, I'm just going to define it as this function for everything except for 6. So now I'm removing that from the domain and saying, well, now if I add it back into the domain, I'm going to just let it be equal to that value of 5, which is what's in that extended function. So again, when you cancel out that factor of x equals 6, the graph you get is the exact same graph, but the hole has been filled. So that's how we deal with those sorts of functions, and that's how we can kind of deal with filling that hole. It's called removable discontinuity. So now let's take a look at how the AP exam might present a question to you. So again, we want to make sure we understand that the AP exam asks you to apply this knowledge that you're gaining from these videos and these rules and these definitions, but they ask you to apply them in new and unique ways. And so being able to extend your understanding to a new situation is a really important skill to be able to have. So here we have example A. A function is continuous on the interval between 3 and 9. So as I look at the table, here are my x values. They go between 3 and 9. Okay, so I am continuous. That's an important piece of information. If I'm told that something is continuous, I want to underline or circle that because that information is not given out lightly. The table below gives values of f of x on the interval. Which statement must be true? Okay, so let's figure it out. F of x crosses the x-axis one time. So let's take a look at what's happening here. So if I were to plot these points, there's my 9. Let's see, 1, 2, 3, 1, 2, 3. I've got 3, negative 2, so that's kind of here. I've got 5, 1. I've got 6, 3. It's kind of up here. I've got 8, 5. So that's up here. And then I've got 9, negative 3. So here's my function, and I'm told that it's continuous. So what that means is from 3 to 9, it must be connected somehow. So I'm just going to kind of connect my dots. It's not very pretty. Okay, so now that's what my graph must look like, and I'm told that it's continuous, so continuous means connected, and I'm going to interpret it that way. And when I'm continuous on an interval, that means there's nothing in there. There's no vertical asymptotes, no holes, no nothing. It's continuous and connected on an interval. So understanding that definition is really clutch right here. So f of x crosses the axis one time. When I look at this graph and how I've connected everything, look, it crossed the x-axis twice. So it started in negative land, went up to positive land, and came down to negative land. So I'm going to cross that guy off. That's not true. Statement 2, f of x crosses 2 times. I'm going to circle that as being yes, true. Let's look at the other ones. F of x crosses the x-axis at least 2 times. Now, that makes me question why I circled 2. Am I sure that it's exactly 2? Well, let's take a look. If I cross exactly 2 times and I'm given points like 3, 5, 6, 8, and 9, and the corresponding y values, I'm missing some y values in there, aren't I? So how do I know for sure that between, for example, x is 6 and x is 8, how am I to be certain that my y values stay up here? How do I know that there's not like some value of 7 where it drops way down to -2 and then comes back up, you know? How do I know that that's not the case? And the answer is, I don't. So this makes me understand that maybe I'm not so sure about circling 2. Oh, I crossed it 2 times, sure, but it doesn't cross exactly. So I'm going to reevaluate my thinking, and I'm going to circle option 3. Because just because I'm given these values doesn't mean those are the only values that exist. There's no way to tell if my graph is going to dip back down and come back up again. So my graph could look like this for all I know. I'm missing some pieces. All I know is that it's connected, and it will for sure cross at least those 2 times. Now, option 4, clearly, I'm going to cross off. I have enough information. And what I've just established is this idea that continuity over an interval means that I'm going to hit every point between my lowest point and my highest point. Notice, every y value was hidden here, okay? So every single y value gets hit between my lowest, and actually my lowest point is here, between my lowest y value and my highest y value, every piece of graph covers all the y's in between. And what we've just established there is something called the Intermediate Value Theorem. Now, we're going to get to that in just a moment, but I just want you to hang on to that nugget. So here's an example. A function f of x is continuous. There's that word again. I'm going to highlight it. Strategies for your exams. On this interval, 0 to 10, if f of 0 is 5 and f of 10 is 20, okay, so f of 0 is 5, 1, 2, 3, 4, 5, and f of 10 is 20, so 10, 20, 0, 5, it's a poorly drawn graph, I apologize. Is there a value x equals c where c is between 0 and 10? Okay, 0 was this x value, 10 was this x value. Okay, so between these, such that f of c is 11. So is there a point somewhere, so here's 0 and here's 10, so c is somewhere in here, okay, that's what this is saying, it's not the endpoints, such that I have a y value at 11. So where's 11? 11 is kind of like right in here. Now, is there a C 11, basically, somewhere in between the 2 points that I plotted? Now, we just talked about this idea of being continuous, and we noted up here in this graph that between my max and my min on the interval, I hit every point in between. Well, if this function is also continuous, doesn't that mean I'm going to hit every point in between? I might hit it like a ton of times, and actually, this is, yeah, it could go below. But the idea is, am I going to hit that value of 11? And the answer here, hopefully as you're looking at this, you're like, well, yeah, that makes sense. I'm continuous and connected on an interval. That means there's no holes, no asymptotes, no jumps, no weird stuff. It's all continuous. And even if I just connected these 2 points with just a straight line, I would hit 11. And so if I have a continuous function on an interval, and notice the interval is closed, then I'm going to hit every single y value between the y values on that interval. So as long as c stays between 0 and 10, I'm going to hit every y value between 5 and 20. And this really is that intermediate value theorem that I mentioned. And this is a really big deal. So what I want you to do is make sure that you copy it down. And if you need to pause it to get it all copied down, you go for it. But I want you to notice that this says a function is continuous on a closed interval, takes on every value between f of a and f of b. That's your intermediate value theorem. And the way you're going to be asked about it on the AP exam is similar to the questions that we established this intermediate value theorem with. And it's a really important concept, and there's 3 theorems that you're going to be responsible for really knowing the definition and really knowing the criteria for. And this is the first of 3. The other 2 are the extreme value theorem. We're going to get to that in Unit 4. And the next one is called the mean value theorem, and we'll get to that eventually as well. But for now, the intermediate value theorem is based on this idea that if you are given a continuous function, you're going to hit every point on an interval between point A and point B. Every y value will be covered. So just like we were connected here in this example, and we established that we were connected here in this example, if this 11 is between 20 and 5, then yeah, it's going to be hit because we have a continuous function on a closed interval. So again, here's that intermediate value theorem. Whoops. And we have some fun examples that we can do with this. And so I'm going to kind of do a couple of little bonus examples here. The first fun example is there a real number that is exactly 1 less than its cube? So is there a real number that is exactly 1 less, so that means subtraction, than x cubed? So if the real number is x, is there a real number such that if I take its cubed minus 1, does that exist? Well, the idea is I'm going to turn this into an equation, and I'm going to use the intermediate value theorem to say that yes, it exists. I don't have to find what it is. I'm not going to do that. But what I'm going to do is I'm going to get it equal to 0. I'm going to say x cubed minus x minus 1 equals 0. Now, I want to know, is this true? Essentially, that's what I'm solving. And using the intermediate value theorem, what I'm going to do is I'm going to show that, well, if my function starts out negative and goes to positive land, then it had to hit 0 in between. Because I know that this is a polynomial, and polynomials are always continuous. So this is a continuous function. So when I prove that something is true, when I use the intermediate value theorem, I need to state the conditions. So step 1, state the conditions. This x cubed minus x minus 1 is continuous. It's a continuous function. And I'm going to say that it's and I'll close the interval off here very soon. But what I'm going to do now is I'm going to find, and I'm going to define this as f of x, just so I don't have to keep writing it. Find where f of x is less than 0 and where f of x is greater than 0. So if I can show that there's something that makes f of x less than 0, I'm going to show that. And if I look at my function, when x is 0, f of 0 is negative 1. I've shown that it's negative. So I've shown that there is something where I am negative. Now I'm going to find one where I'm going to be positive, and I'm going to plug in 2, f of 2. Well, that's 8 minus 2 minus 1, that's just going to be 5. I've shown that I've gone from negative to positive, and I'm going to show that this is a continuous interval or a continuous function on the interval 0 to 2. Those are the values that I chose. This is a continuous function on the interval 0 to 2. And then I'm going to state my justification. Justify. Since f of 0 equals negative 1 and f of 2 equals positive 5, and here's the best part, once I've said it's continuous on the interval, I can just say by the intermediate value theorem, there is some value such that f of c must equal 0. And then you got to say that c is going to be between 0 and 2. Okay. Therefore, yes, there, I'm going to run out of room, is a real number such that x equals x cubed minus 1. Ta-da! So this is how you're going to apply that. And I'm not going to use that same rationale here for this last example, but to prove that you have at least one solution, for this example here, it's you're going to do it the same way. You're going to take and you're going to say, well, 2 to the negative x minus x equals 0. Call it a function, f of x. You're going to find where f of x is less than 1 or less than 0. You're going to find where f of x is greater than 0. Another way to show it is on the graph. So graphically, if I'm looking at this example, I'm going to graph that function. I'm going to get it equal to 0. And I'm going to show that on my graph, I go from positive to negative. So yes, there's at least one place where this function, by the intermediate value theorem, crosses the x-axis. Therefore, there's at least one solution. And you're going to see this pop up on the AP exam. They ask questions about this all the time. You need to find a 0 of a function. And so if this is your function, f of x equals 0, somewhere by the intermediate value theorem, because the graph of f of x goes from negative to positive. So you can justify that something exists by the intermediate value theorem because, hey, you're negative to the left, you're positive to the right. You have to have somewhere where I hit 0. So this is a really key thing to know. It will show up on your AP exam, I promise you, and if it doesn't, well then I'm going to lose a bet. So, but I'm willing to bet lots and lots of money that you will see this on your AP exam, and it will be a big part of it, and you'll need to know it to get credit on that question. So again, as always with these videos, please know that mastery is not expected on the first try. This is something that is brand new to you, so maybe you need to go back and rewatch the video. Maybe you just need to kind of review a couple of parts and to get everything down. You can always come back to these as helpful tips if you didn't catch everything the first time around. And you guys, you can do this. You know, it's tough stuff, but you're here and you're up for the challenge. You can do this, and I'm here for you, and I have faith in you, and you've got this.